do residential. This is what you will typically see with our residential area is, man, that's
Okay, this is Peter. That's Peter, and his job is a technician for, I don't know if we want to talk about
It's
Metro.
the fiber optic internet installation, basically.
He's the guy that makes the communications happen. I told him, we got to bring this thing over here and take a look at, well, I just want to learn how it works. And I'm not smart enough to know the answers, but I'm smart enough to ask the questions. So that's what today's about. We're just going to ask questions. We're just normal people, but I wanted to record this. So we'll share whatever comes out to be like maybe useful. So here we go. Looks like you laid it out some way that was supposed to.
Yeah. So this is typically what I have to deal with the different fiber optic cables. This is our indoor fiber where we put it on the inside. This is this one in particular is UV rated, and so
you mean the shielding?
The shielding is UV rated. Yeah. Right here is the Kevlar. And it actually like strengthens so that when you
yellow stuff.
When you pull it, it doesn't come. The fiber optic doesn't come and break.
You're saying the yellow stuff?
Yeah, I can strip it back for you.
It's much more fine, right? Like
yeah, that's Kevlar.
And then right in the middle somewhere is where I'm not supposed to touch it.
No, you can. Yeah. So what people don't understand about fiber is that you can bend it every which way, so long as it's not like a hard bend or like a full on.
Okay, how far can I bend this before?
Yeah, so what would you say the hard bend?
Okay, so this you can do that.
Okay.
That does no damage to the fiber.
Because the glass, the radius, you can curve that glass inside.
It's pretty tight.
Okay, what's the diameter of the glass inside?
Well, it is. You strip that back.
Nice.
So that's the Kevlar, and that's the fiber optic. It's shielded right now.
Oh, okay.
So it has like an outer coating that you strip back,
Nice.
and then the fiber itself is really small. It's really hard to see.
Yeah.
It's tiny,
We've got a good view on it.
And even that also has a very thin coating, so that you strip it back even further. That little like
I didn't know that.
little plastic coating that covers the fiber helps keep the optics inside, if that makes sense.
Okay.
Because when the light shoots through, what happens is that you get a light loss because the light shoots every which direction. And so what they do is that they coat the glass in a very, very, very thin film of like plastic. And this is
All right, how thick is it? It's a quiz.
that is a great question. I don't think on the top of my head I remember.
Okay, it's 0.11 millimeters. And then with the yellow on it, 0.87 millimeters.
I think on the cable itself it actually mentions the diameter. Right. Yeah, I got 3 millimeters.
Oh, they took, wait, mil is different.
Millimeters, sorry. It says 3 mm.
Oh, so that's referring to the whole situation.
Yeah, so that whole thing
Okay,
is 3
2.8, probably 3 is the maximum allowable when it has its undulations of extrusion.
Yeah, so this is the indoor fiber. And like I said, this is Kevlar right here. This is a strengthening agent. It helps with pulling things so that when we're tugging it like that, this fiber does not break. So it can withstand a certain stress level, but not that high enough stress level. So that's why we add the Kevlar. This right here is the rock fiber, we call it. It is sandwiched between two fiber optic, not fiber optic. It's 2 fiberglass rods. And so this is how we open it up. peel that back, you can see the fiber. Oh gosh. Yep, and there goes everything. But that's the fiber that's just sandwiched in between, and there's this is basically almost like glued together. And again, like this rock fiber can bend pretty far, but it's stiffer than the other one. And this is actually for our direct burial. So this is rated to be just sat in the ground. It does no damage to it whatsoever. This can be exposed to all sorts of elements, no damage whatsoever. The only damage that you might get is if you actually bend it like that, and that's what we call a where the fiber is bent. And that's the only downside with this kind of fiber. It's flat because this is the easiest way for us to transport it, to like run out into the field and
even when you
it.
coil it, it chooses a direction to form a coil.
Exactly.
And you know that you haven't twisted and then pulled.
Exactly.
Nice.
Exactly. So we also have like other cable. So this is just a single mode fiber. We actually have cable that is like 12 count microfibers. And so it has smaller shielding than this. So it's like when you strip back this shielding, it's almost as if it's like painted. So it's these fibers exposed, but they're painted different colors.
What do you mean? Like this is clear paint, or?
Yeah, so you know the coating, what happened when I stripped back here. Oh, well, it broke. Yeah, you gotta be careful of glass.
You have, is that the tool you always use for this?
Yes.
Okay, but you can tell when
You see that little tufts? So typically for the microfibers, that is coated with like a color code, so that we know which fiber is which. And there's
if you lay that against the dark, can you lay that on the?
Yep.
Okay, so if you see this junk material, you're still sure that you haven't broken it, or?
Oh yeah.
Are there any cases where the glass will get like cracked but not fall apart?
Oh yeah.
Like
we've actually had that. Yeah.
Okay. But that seems really hard to detect.
Sometimes it is, but you'll understand when I say that it's not difficult to detect when you pull it apart.
Yeah.
Because that. Yep.
Okay, I'm gonna hit the video pause real quick.
Yep.
All good.
So what we're looking at is fiber optic lines, and when me, just as an ordinary consumer, this is how I understand the system. You have the input junction that is coming from outside of the house, and all I know is that these lines with the green tabs, these are pre-manufactured with a specific length, and that can be built in bulk and then just passed to us. But so imagine this white line is the one that he's working with, Peter's working with, and he just showed us this white line that's sun rated but not ground rated, I guess. And then inside of here, maybe we'll open it up later, but so this comes in from outdoors, and then to set up whatever I have in my establishment is going to be using these pre-made ones, which saves, I guess, the effort of what we'll see, which is splicing lines. And then, so it comes from the junction to a modem, and then you have your ordinary, nothing changes between having fiber or having cable after that setup. And so router, modem, etc., there's nothing novel about that. Switching to fiber includes these two gadgets. Okay, Peter, what did I miss?
No, that's pretty good. Yeah, I actually agree with that, and then I can show you like the rest of what.
Okay, while Peter gets that stuff ready, I just wanted to mention what I see here is a polka yoke. That's a Japanese term for in manufacturing, where you have a situation that basically prevents failure and makes it not possible to proceed if you enter a certain condition. So these little sticks, they've added something to make them rigid, and so they snap instead of bend. And the manufacturer designed it so that the snapping happens before the radius where you would, at some radius, this little glass fiber will crack. And before that gets reached, these stiff fibers are going to crack. And then it is like extremely evident. Wow, that's really tough.
Yeah.
It's very evident when it happens. It is so detectable, and you couldn't like accidentally, oh, okay, well here they kind of, maybe if you manipulate it by hand, you'd see it looking straight. But boy, like it's very, you could feel it just by stringing your fingers along. You wouldn't get that indicator with just the glass alone. Okay. Here on the outside of the house, to just quickly show where the fiber comes in, they installed this only about a year ago. And that's crazy because I lived in Malaysia in 2020. We already had fiber inside the home. And I'm noticing like the neighborhood here in America, we don't have it yet. I was confused. And it comes down to actually the complexity of building new developments and then interfacing the new infrastructure with what already exists gets very complicated. And so I'm sure new developments here maybe had fiber first, but in my experience, it happened in Asia first. So this is, I don't even know what to call this terminal box, but it's basically, I think, just to protect the connection. And then the black wire that Peter was talking about here, and the white wire that goes into the home. It looks like it's at risk of bending too sharply here.
Yeah.
And that's half the installer's fault, half my fault, because I think I booted them out when I was having a bad time, and I think they just did the initial put it together. Anyway, I think we can open up this box, Peter, right? That was not even a legit.
No,
we won't talk about how to. Okay, so what happens?
Yeah, so inside, this is how we secure the rock fiber. This is what we call a house box. And inside, this is the rock fiber comes in. We split this off and we clamp it down by friction fit. And so we screw that up. This just protects the fiber on the inside when we coil it, and this just loops around right here. This is something extra. You probably haven't seen it, but it's probably inside that little box that you mentioned. This is just a connection. So those little manufactured connection points can connect into here if we decide to just use connection points instead of just splice the fiber just like this. Now, if you see right here that this indoor fiber is not secure, normally we secure it to this tray right here. And like you said, this also needs just people to come back. I could come back.
Maybe we can do some cleanup later. What's the purpose of all these? All that extra length?
It is so that we have that length to come down the splice, because when we splice, we take
you mean
away
just the access to hold it in your hands or have it on
a tray or something? Exactly. Okay. Yeah. And this is the heat shrink that the splice stays in.
The metal?
Yeah, the metal is to reinforce it so that.
Oh, you mean there's the splice underneath that heat shrink and metal?
Yes.
That's what the technician did.
Yep. Okay. And I'll demonstrate that in just a little bit. But yeah, that's pretty much it. The way I would also secure this was, if I wrap this wire this way, I would put like a screw clip here and a screw clip here to kind of like streamline it up.
I guess we'll do that. Cool. Well, as a mechanical engineer, I can show you this is just a hexagon. So the key is not for security. If you have a hexagon or a part of a hexagon, you can open it yourself. I assume that the purpose is not security. Don't worry about the key situation. Okay,
talking about my job.
Where this came from was all the way up at the pole, and part of me having a bad time was excessive amount of construction going on with the changes. So this is the pole which carries all the electrical lines and stuff. Oh, we could get into the rentals and stuff and who owns the pole. All of the borrowing and exchange between contractors and service providers is part of the situation that causes difficulties and slowdowns. But oh, Peter, you might as well come over. The big splice for my block is out here somewhere. We'll talk about that later. So we had so much construction for months going on here that I got the impression that these lines, this line here was feeding my whole block to the dead end down the street. And so am I understanding that correct? Like,
Oh,
yeah, you're allowed to.
yeah. Sorry about that.
Or do you not want? Okay, so this is an answer coming out. So I was asking, well, why did we have so much construction happening right here at this corner when I thought we were just getting one fiber line to each home?
Yeah, it's so basically with a brand new installation, there's a guide wire that is strand across pole to pole. So that is a lot cheaper than if you were to just put like hooks on each of the poles itself. Like we're basically paying for the same thing if we put hooks or if we put a new wire. Now they have to stretch that wire across each pole and then ground it. Then that's probably what you're dealing with. It's just all the construction to anchor that guide wire down on the ground.
Yeah, they did inform me that just by adding the weight of one cable down the block, this pole had to receive an extra ground anchor, not grounding as an electrical grounding, but as in a tension opposition. So there's some tension coming this way that tugs on the pole and they have to oppose it going that. So that's why you see these poles with like 4 different cables coming down into the ground. They look like they're doing the same job. Why don't they just have one? It's because they changed their mind later. I want to refer back to, okay, this is what you were looking at before,
Yeah.
and when we take it off, you get that.
Yeah. So what as a tech, what we don't want is see these extra points of possible failure.
So you mean basically connection A, connection B.
Correct. So what we don't want is that we don't want multiple of these connection points to be a potential source of failure. Because
so if they spliced the other end of this guy
Correct.
outdoors, they could have had a direct connector put on there and not have and eliminate this splice?
or even go from here directly into here. I don't know why they couldn't unplug that and just plug it into there.
Well, that may have been me because I told them I wanted to be able to change stuff or change the length.
Oh. Okay, that
Probably
that may
still
have been
negated because we could just have some extra length around here.
Yeah, but this is a potential light loss, and this is potential light loss, and so the splice outside is also a potential light loss because this is exposed and it's not a continual length. If that makes sense.
Okay, when he says light loss, he's talking about loss of the light traveling inside the fiber, not like a small amount of loss, right?
Yes,
Light loss.
because it's laser light that's shooting through here, and so you need to contain as much as possible. So
Okay.
any imperfection is gonna cause light loss. All right, so now that we get to the splicing, so we're gonna start with the rock fiber, and here we strip it back. So there's several notches on here that enable me to strip back. These are manufactured so that they're the exact diameter of which of what I'm
Three
actually
options. You mean you have 3 diameter options, and these are, dude, I need to get it. Where could I get
They
it?
they come with the splicing kit. So this splicing
Man,
kit.
of course they don't want us to have good tools. Okay, sorry.
Yeah, so I don't know exactly what the dimensions of this, but they're a perfect notch fit.
Is there a brand and model on?
Yeah.
Oh yeah. Okay, so it's a Pros Kit 8-pack 326. Nice.
I'm pretty sure you can also order these. So
Yeah.
That's not gonna be a big
I'm gonna
deal.
look it up later.
So the biggest size strips back this sheath, so that's what I mentioned there. And then the smaller size, the next size down, strips back this sheath, this plastic sheath. And then the smallest size strips back the plastic layer that comes surrounding the optical fiber. And you try to get it as clean as possible, so we take an alcohol wipe and we make sure we don't damage the fiber, but you fold it like that and you should hear like a squeak.
Ooh, beautiful squeak. Do that one more time.
Yeah, and that's how you know that it is clean. Oh, well, I just broke it.
Well, now you know how fragile it is. Is that piece, where was the piece you broke off? Hang on.
It is right here.
Okay, I want to do something.
Small.
We're going to interrupt this video with a quick experiment by David. I can't pick it up. Oh wait, no, I got it. All right, so I want to know, can I bend this around a 1/4 inch diameter? And no.
Nope.
Okay, so 1/4 inch cannot survive. And then to compare, this is that carbon fiber. I showed you this in another video. And it also has a fragileness to it. Extremely strong in tension, but not able to be bent. If you pinch it, this is multiple fibers, but it's not exactly a fair test. Darn it. It always just breaks when I don't want it to. All right, so if I twist it up in my fingers. All right, so the answer was yes, this definitely could wrap around a 1/4 inch radius. But I bet if this was one single strand with the same thickness, that 0.11 millimeters as the glass, then this would not survive either. Both of them deep down, these materials are brittle. Okay, back to the normal show.
Yeah. So you would hear that squeak of the fiber as I clean it, and then I bring this cutting machine to it. There's several grooves in this cutting machine right here. I choose the middle one because that is typically what I use for this size of fiber. You clamp it down, and this tool cuts it at a 90-degree angle. And so that's why I put it at this, because we're going to need that for welding. So
What's the 90-degree angle?
yeah, so this is a diamond blade.
Oh,
It cuts the glass at a 90-degree angle. And sometimes it cuts it clean, sometimes it doesn't. And you'll see whether or not this actually works when it cuts it clean.
this is our pointing tool. You said diamond blade, diamond coating, probably on a steel wheel, and
Yep.
then 90 degrees between here.
And I just cut it
here.
right there. So I've already cut the glass, and so I can actually pick up that little bit of glass right there. So that is cut glass.
Where'd it go?
You can't see.
Okay.
I think
Wait,
I
I
lost
found.
it.
I found. By the way, this board, this plastic board, has a.
There it is.
No, go back down to
Right there.
the focus of the camera
Oh,
is
is
going
it?
straight to the plane. So
Gotcha.
okay.
I can't see it.
Well, yeah, it's very tiny right there. There.
Oh, we found it. Wait. There it is. All right. Are we ready to go back to the machine?
Yeah.
Okay.
So the machine has cut the fiber at a 90-degree angle. I make sure I do not disrupt that clean cut. So I pinch it down like that, flip it up, and then I just gently lift the fiber up like that without touching anything. And then I put it on my machine. So this machine is a arc welder. It has 2 prongs in the middle of it that enable the weld to happen. So the way I would put the fiber in is that I hold it, pinching it like this. I flip this flap up, and this flap just holds it in place as I gently lay it within the groove that's down right here. This is where the arc happens. It's very small, as you can see. It doesn't require that much energy either. it's calibrated so that when it arcs, it just welds the glass as is, which is very minute, mind you. So I clamp that down, and then that's the first half. And I'll quickly do the other half of it with this connection head. Now this connection head is what you saw outside. I'll explain what this connection head is later, but this is the other half. I strip it back, strip off the coating, find my alcohol wipe, make sure you hear that squeak, grab the cutter, cut it at a 90-degree angle, lift it up very gently.
Oh, that cut happens very fast.
Oh, yes. And then what you want is to put on this sleeve. I typically put on this heat shrink sleeve, and that's what you saw on the outside. This will ensure that the fiber that is spliced is protected, and there's a metal rod in there for structure. And you'll see that in just a moment. Now, we put this other fiber in, just like that. It's very small, and then we close this. Now, turn on the machine, and you'll see in a moment what the fiber actually looks like. This gives you a closer up view. So the top screen is going to show the fiber from the top angle.
Can I adjust for glare?
Yep. So the top screen will show the fiber from the top view, and the bottom screen will show the fiber from the bottom.
Nice.
So it shows it at both angles. We set it. Okay, so now it's trying to calibrate where it's at. So you see right away, there's this kind of chip where the blade did not cut clean.
Oh, hold up. Let me get the view close as we can.
Yep. So right now it's not in focus. I have to readjust the fiber to put it in focus. But right away I can see there's a potential problem. One, so this fiber on the right side is perfectly well. It's perfectly straight. There's nothing wrong with the core in between.
The white zone is...
Yes. Oh, yes. Let me explain. So this right here is the entirety of the fiber, but inside the fiber there's a core. So there's actually 3 layers to the fiber. One is that thin film that surrounds the fiber.
Okay, so I want to say that basically this dimension is the 1.1 millimeters we measured earlier.
Yes.
That.
Yep. That
And then
dimension.
this is a whole. Is it literally a void?
No. This is a protective glass coating and a glass rod inside the glass.
Double glass. Okay.
And this is to ensure that there's no light loss within the fiber, because the light bounces around inside the core. And so even if there is like light that leaks out, because of this extra cylinder, it will bounce back into it, still projecting the same amount of light.
Dude. Okay, so basically if you had like a tube and you shined a light bulb in there and then you covered it up really quick, it would keep on bouncing around.
Correct.
Okay.
This is the same effect with light refraction, is that when you have like light within water, you'll see that the light shoots inside this glass membrane at first, but when it hits that refraction of the water at the right angle, then it reflects off again. So that's what this glass is mimicking.
Okay.
But as I was saying before, is that you can see that there is a bit of like stub in between. So I'm going to take that off. So it's kind of hard to see. I'm gonna have to go back.
Pause the camera for a sec.
Yeah, that's perfect. All right, so I set the settings of this machine so that it pauses every time that I may see a default and I may want to interrupt that. So right here, both sides look very good. They line themselves up, and this machine adjusts it so that the alignment is perfect for the weld. You notice that I get an error. That's because the machine is detecting that there's slight warping inside the core itself. So the core itself It's important because that's where the light is traveling through. And you see that's where the cracking you were mentioning is that there's a slight defect. But as you'll see, once we set this machine and start the weld, that I don't pay attention to that because that usually fixes itself.
What about the one farther back along the edge here where that's not going to be righted?
Yeah, that is still within the realm of the arc.
Cool.
So you'll see in just a moment, the arc will splice both of these in a very uniform fashion. Hopefully that the arc is calibrated correctly.
Maybe should we get a countdown or something? So, are you just about to press this?
I'm just about to press it. Yes.
Okay.
So 3, 2, 1. Oh, okay. There we go. Oh, that's not good. Okay,
Splice
so
completed, lost.
Yes.
Oh, it even tested it instantly.
exactly.
Whoa.
So there's a light that's shining directly up through this splice to see the splice loss level.
Oh, it's shining this whole time, and that's part of the reason we can see everything.
Correct.
Okay.
And this is the type the loss ratio that we want. The 0.03 is the maximum threshold that we are allowed before we have to resplice. If this was 0.04, we'd have to take apart the splice and resplice it till we get 0.03 or lower.
So to someone like me who's kind of a layman, what 0.3 or
It's the,
just seems kind of arbitrary. Like why that number?
Because that number, so you notice it's in dB. dB is what we measure in light levels. So that's the level of light in which the machine can pick up the light.
Right.
So our threshold of light levels that the machine that was just shown shows has a threshold of 8.0 to all the way to it's in the negatives. So it's negative 8.0 all the way to negative 28. When it hits negative 28 or past, the machine will no longer pick up the necessary information packet, and you won't have internet.
Okay.
Yeah. Now, why does the 0.03 matter? It's because that if you get any more loss than 0.03, then you could get a whole level of light loss within the splice. So this is when we're in the technician field, when we're looking for problems. This is typically the failure point, the splice point, is one of the first problems that we look at.
Okay, so I've got from the electrical point of view, this is an attenuation just like you would have in an antenna that's picking up electromagnetic fields. We do experiments where we'll transmit from a Wi-Fi device or a radio device to another. We measure the attenuation in losses, so it is negative, but since we said lost, and the positive number is displayed. My question is now, signal to noise ratio is a big deal for communication over the air. Is it possible that noise could be injected if you had a damage on the jacket?
If the damage is not to the fiber itself, no. If the damage is to the fiber itself, then yes. The reason why we're concerned about this is because whenever the temperature is our biggest issue, is that whenever the temperature rises, the fiber actually expands and contracts, just like everything else. But when it expands and contracts to an imperfect weld, that will break the weld. So the fiber is kind of brittle in that area. And so if this arc is not good, then in colder or hotter climates, it will expand or contract and then break the fiber, severing your connection to internet.
You mean immediately after the weld, or you mean after it's put in service?
After it's put in service.
Okay.
Yeah, so this service could be good until it is tested through like either heat or cold, where the glass itself expands and contracts. So right now, what I'm looking at is there's this very small defect, and I got within my parameters, so 0.03. But I just want to have that insurance, so I just press arc.
So
again.
you're not looking at that defect?
No, because that defect is not going to tell me much of here, because this is a continual
So you mean
piece.
just you're not pleased with the look of this zone?
Exactly.
Okay.
Exactly. So I'm going to press arc again, and it's going to re-arc it.
Nice.
And you see it brought it down.
Definitely improved.
Brought it down to 0.02.
Oh, cool. So we have a visual improvement. Now I can barely see the issue, and then they do the measurement improvement. Okay.
Yes, but this comes with its own risk. Every time you re-arc it, you brittle up the glass itself. So that's why it's important that you get the arc right the first time. And then what I typically allow is for one more arc before I just re-splice the whole thing. Because if after that first weld, if it's not good, then after the second weld and it's still not good, it's gonna be brittle every time you arc it again and again and again.
Okay, I'm gonna pause. All right, so what happens next?
So what we're going to do is that once I flip over this lid, the motors are going to retract. And while retracting, they're going to pull apart the fiber that is right here that we just welded in order to test the strength of the weld itself. So do that, and these motors pull apart.
Could we maybe switch sides?
Yes.
Okay, the light's better on this side.
The motors pull apart. My fiber did not break.
Hold up, you say motors pull apart.
Yep.
Can you
These two are the motors. So these two adjust either however which way in order for the fibers to line up perfectly. Oh, and careful about this. Yeah.
Sorry, I sort of understand that.
Yeah. So this whole machine is calibrated so that these two arms of the motors line up the fiber just so.
Oh, you mean in which direction did this motor just move?
This motor moved that way, and this motor moved that way when I opened this flap in order to pull the fiber.
Did they stay clamped, or they just gave space?
Nope, they stay clamped.
So now there's actual tension on there right now.
Correct.
Oh, okay.
So the fiber itself is actually really good at tension. It's just really bad at inflection, which is the bin that you put into the fiber itself.
Got it.
And like I was saying, these machines itself are calibrated so that they don't overpull the fiber, or they don't damage the fiber, or when they're lining up the fiber, they actually do their job. That's why this machine is so expensive. I think this machine's like $5,000.
Not surprised. I think I remember back in undergrad days, somebody talked about like 10 or 20 grand for one of these, and yeah,
It's possible. I heard it was $5,000. Anyway, so if you don't mind holding,
I'm sure the price has come down.
Here?
yeah, just right there. All right. So I bring the sleeve up and I hold it down like right here. So that when I flip this up and flip this up, the fiber doesn't just come off. It doesn't just fly off. And so now you can still hold on to that. That's fine.
Yeah.
So right now the fiber is still strong. And then I slide the sleeve over, and that protects the splice that's right there. Because even though that the fiber is spliced in, it's still vulnerable to outside elements because it doesn't also have this coating anymore.
And that'll
So-
help prevent bends. And
Correct.
There, yeah.
Yep. And this is the
Well, look.
the heat chamber right here.
Hold on. I want to watch this happen.
So as you notice that I don't have the other half of that, and that's because the pin that was in here,
Feature?
yeah, the pin that was attached to here was it fell off somewhere, so I don't have a replacement pin. So in order for this to the heat shrink to actually work, this is a hot box, by the way, a miniature hot box. I press the heat twice in order for this heat shrink to fully melt.
You can feel it's warm, yeah, just barely.
Yep, and it
Plus-
also says like it reaches about 250 Celsius.
Got it.
So I wait for that to finish, and then it's nice and gooey. And what I do is that I wait for that to cool. I do this so it cools faster, but these ends right here, I make sure that there's no hard bends in it as I allow this to cool down. I turn off my machine so that I save battery power for the next splice that I do.
Oh, wow. I forgot entirely that this is all running on a battery. That's a lot of action going on. Is the battery removable from this unit?
Yes, it is actually.
So it's kind of like one of the old video cameras.
That's good. Yeah, so this battery actually comes out right here. Somehow? Kind of forgot.
But it's not something you ordinarily do.
No, I just...
Because you can just charge it while it's in the unit.
Yep, there it is. So that battery pops out just like that.
Oh, no.
There you go.
Well, we know it's not a Windows machine because you can shut it down that fast. Okay, this is a public service announcement. Peter was going to tell us about safety.
Yes. So I wouldn't normally, I'm pretty experienced, but I would normally wear safety glasses to this, especially if you're not experienced. You definitely want to wear safety glasses because there is a risk that when you actually strip back the fiber, splice it, and it breaks on you, it actually breaks into your eye. You can also get these like tiny shards into your skin and they just break off in your skin. So that's...
I want to jump in.
Yeah.
All right, so this is like where I'm familiar. This fiberglass fabric that you would get for bodywork, etc., has the same safety issues. And so, yeah, they can definitely prick your skin or get embedded. You'll get itchy and maybe worse things. And also, I was going to see if I can measure the... This is a cluster of fibers, but just to compare, I want to clamp the my multimeter. Measures how many meters are in my. Okay, so this if I squish it, I'm getting 0.09. Okay, so this cluster laid flat is just slightly smaller than. Yeah, I'm sure this is more hazardous than one single strand, but there's a relationship. Okay.
Yeah, so I was going to talk about this right here. So this is pre-manufactured. What it is it aligns the fiber in such a way that enables the connection to be flawless without a splice. That's why this, and this is bulky so that it is easier for us to plug in and plug out. This is what you would typically see inside a terminal, is that we have mainline fiber coming into the terminal, and this port, this line fits out perfectly so that it clicks into place, causing minimal loss without splicing it in. And I have a photo here showing inside that terminal. Now this is quite the mess.
Should we come to your side?
No, it's fine. You can show it from this angle. This is like inside one of the terminals that he was showing you up in the air. So this is the aerial terminal. Right now, this is multiple drops configured and spliced in. This is not typical. Typically, it is much neater than all this, but this is one of the problems that I typically face inside the terminal. And as you can see, that these lines right here are connected into one of these, and that is connected into a splitter. So this is a two-way splitter split from one. So this splits the one fiber into two.
Is it possible to use this welding tool to make the splitter as well?
So these splitters are pre-manufactured.
Got it. Okay, so very precise alignment to put two lines into one, but you just have to do 3 splices to build that, right?
Right, because this right here splits that one fiber into 2, and inside the terminal itself, it's hard to see from this angle, but it splits it into 4. So there's a 4-way splitter on each of these nodules. So these are 4 apiece.
So what I'm picturing is that you have this junction that has the two coming into one, and then you have a box. And out in the field, it's doable to make this junction to a line, and this junction to a line, and this junction to a line. But that one's way more sensitive and probably it's difficult, and you would not do this part in the field. Yeah?
Correct, except that this box itself is pre-manufactured. So you don't even have to worry about that point, or that point.
Oh, so at the end of this black deal, the one that then it has its own green plugs?
Some of them do. Now I finally understand what you were trying to say. Yes, and we do have to splice in at those points as well.
This is a field-made splice, or this is a manufactured splice?
So this is manufactured. So this,
even the white part.
Yeah, so that white part's manufactured, but it has a long tail. So this won't be right up against the box itself. It'll come outside the box. It'll be a very extended long tail outside the box, so that it would be easier for us to coil up and to splice.
Got it.
Now, the cool thing about these little heads is that inside this box right here, the fiber comes in and it's at an angle like that. And so when you connect it up to another head, the other head actually connects diagonally with that fiber. And so
super hard to control the orientation of that.
Correct.
But I guess it's
pre-manufactured.
Okay.
So what they do is they make sure that this little tip right here coming out that little tip is where this junction is at. So that diagonal is where this tip on that white part comes out. And so when you plug this part in, it meets up with a pre-manufactured fiber inside here that meets that fiber just like that. So when you hear that click inside here, you know that that is clicking into place. And they are very close together. They're not like a millimeter apart. They're really close together, but they're not welded. So that's why it's important.
So there's a much bigger loss that happens for every single time you add one of these into your circuit.
That is correct. But
Do you
the
call
loss,
it a circuit?
Yes,
Can we
can call it a circuit. Yes, and that's correct. Also, another thing that happens is that dirt can pile up inside here. So that's why we keep this part covered and we clean it. We have cleaning pins that actually help with making sure that these are not covered in dirt or whatnot.
So we covered the terminal.
Yeah, so that's the terminal. This is this is the underground terminal that I deal with. The fibers come in and they go into this cylinder right here. And here's another picture. Oh, that's okay. And this is the box that it comes in. So this is what we do for underground work. So what was presented earlier was the overhead work. So that's everything that goes on a pole. This is everything that goes underground. It comes into a box here. We have conduit that is buried underneath. And inside this box here is that terminal that you saw. This is our hut, mind you. This is the internet hut. So these are what we call augments that each of those augments is like the old day telephones where you have to like unplug and plug it in to each and every port. Each and every one of these hosts at least 1 to 2 terminals.
So you're saying like this is an occupied augment and this is an available augment?
Correct.
Okay.
Correct. And this is all going to a server hub, and from that server hub, it shines the light to these augments. These augments go straight to the terminals that I was showing.
Okay, but unlike electricity, for every single yellow cable here, there's a
potential light loss. Yes.
well, no, I mean there's another yellow strand, or there's another strand of glass going to the other end of where it's connected.
Correct.
To the server. So you can, if you were adding more here, and then your, what do they call it? The cable, underground cable only has a certain number of terminals, strands available, then that's how many you get. And so every time they bury a cable, I assume that there's way more than you need.
Yes. And also, I was going to show it here. So this is inside that terminal. This is looking from where the mainline fibers meet the splitter fibers at the terminal. It's
so
kind of
be
hard
like,
to see.
At the end of the block, under the ground, or
This is underground. So this is the underground terminal. This is the mainline fiber coming in on right here, and this is that splice I was showing you coming out.
with
As you can see, there's quite the difference because this is microfiber that's coming in.
microfiber. What does that mean?
Microfiber is it's almost as small as a human hair.
So it's also a glass fiber, but smaller than
It's
the ones
smaller.
we're looking at right now.
What we showed earlier when we stripped back this fiber to its bare minimum, when I was mentioning the different color coded fiber, that is what I'm talking about.
Oh, different girths.
Yes, and so this is just an outside coating right here that protects the fiber. This fiber does not have this outside coating. We call this fiber microfiber because it can fit into a smaller space.
Okay.
And so when we strip this back, it's very fine. It's also it's brittler than this fiber right here.
Okay.
Is that a smaller diameter too, so that it can actually fit into ribbons. So this fiber can fit into a ribbon the size of this. So imagine, let's see, how many fibers? 12. Imagine 12 fibers lined up, row to row, in a
You
ribbon.
mean they're all in one plane?
They're all in one
okay,
plane,
got
yes. Row to row, in this area. And then you have, in our 64 count or 128 count fiber, you have a bunch of these ribbons stacked on top of each other in order to fit a cable that's about this size and diameter.
Oh, so you're saying like a ribbon is a row. You said the exact number, right?
It's 12, yeah.
So 12 here. And then that's encased.
Correct.
And then there'll be several of those.
Correct. To make a 128 count.
128 circles. Okay,
Yep.
got it. That's not a zero.
And that's what's being serviced at the internet hut, is that in this hut, in the back is the ribbon fiber, and it goes to, we use about half. There's so many fibers that come to the hut that's just extra.
So a hut is an outdoor thing that's out in the community, or this is not, you don't see a hut until you go to the property of the main, like the branch of the
So this
business.
is the hut for the district. So for the district of this area, for this entire community, all that internet lines run directly into this very cool air-conditioned hut.
A district would probably serve the entire College Station.
Correct.
Okay, got it. That means once they set up this infrastructure, only one big fat fiber line has to go from that hut to the server.
They have a loop. So they have, because redundancy is the best policy. So in the fiber optic loop, so you have like the community, and so here is the internet hut. And so what would happen is that you have a loop, we call this A side, and then you have another loop, we call this Z side. So it forms a giant ring that branches off into all the different communities.
You mean like a neighborhood, or you
And around the entire city.
Okay.
So this is around the entire city. And it's how it's
That's
choreographed.
what you meant by giant loop. Okay.
Yep. And each of the branches is one of the mainline terminals that I was showing you coming off the main branch. But this main branch, we call this portion A side, and we call this other portion going backwards Z side. So if A side does not work for whatever reason, we have the other backup, Z
They
side.
can serve the service
Yep.
to the entire rest of the loop.
And from the hut itself, we actually have internet coming to it. So in the larger, like nationwide scale, we actually do also have coming from into the hut A side and Z side from the entire country.
Got it.
Wow.
So in case that A side is like messing up, then we have Z side. At one point when we were starting out in this city, we actually did have problems with A side, and that's why there's so many ports on this and so many ports open, is because if you could see here, this is labeled A side and this is labeled Z side.
And why did you call it a port instead of that last term that you
Oh,
used?
augments.
Augment,
Yeah, I use them interchangeably. So I call these specific ports. They're also known as augments.
Got
So
it.
the augments is specific to each individual connection.
Okay, so if you caught on, this little hut is such a small word, but this isn't like a Pizza Hut. This is like a big piece of infrastructure, just small in size. And we said the whole city may be in here, and I don't know if you mean in some cases counties, like Brazos County, but
I could actually show a map too. All right, so this is what I'm talking about when I say citywide. So the hut right here services a giant loop. So this loop goes through all these like different parts of the neighborhood, makes this giant ring. So we call that part of the ring A side, going one way, and then going the opposite way, we call this Z side. So A side would, so basically it's almost like two giant rings that go around the entire city that we branch off from that main line into every single individual neighborhood.
no, the places where there's branches, those aren't called huts, right? Those are
Those
are called what?
there's one internet hut that is being serviced for the entire city.
But what do you call the things that branch off?
We would still call it part of the main line. So this is the main line, and then the main line goes into the terminals to each individual neighborhood. That terminal services,
Neighborhood terminal is what I might call it, yeah?
yes.
Okay.
The way it would work is that from the main line, it would go to separators. It would go into separators. So it would go into these giant boxes that separate the fibers into the different branches. So it would be in a box. I'm trying to think of. It's a giant box, a cylinder that has a whole bunch of just splice in between. It splits them off into the different main lines that go to the different neighborhoods.
Got it.
Sorry.
Okay, and that's what, something like a meter, there's something that comes up to your belly or something?
This is like the terminals I was showing earlier.
Okay.
It
the
looks
gray one.
just like that.
All right.
So nothing too crazy. It would look just like this right here, where
Oh, okay.
it's just a longer version of this right here.
So now I can see the scale of it compared with that connector.
Yep.
Oops.
Yep, that's the other part of the terminal. So that's where the connection points hid inside that terminal. This terminal is not very big. The bigger version for the splitter is a longer version of this right here.
Got it.
So that it's just a bunch of splices spliced in, and that's all that is when the main line comes in and it splits off into more main lines.
The question I just asked was like, first it was, does this machine do any other function? And then we got onto evaluating. So this is capable of evaluating losses on old connections, but he said, sorry, where did we go after that?
Yeah, so I was just discussing that this machine itself, it splices together the fiber. That's all it does. It's just the very simplistic single mode fiber. There are other machines that splice together the ribbon fiber together. So you strip back the ribbon fiber and it splices the individual microfibers together all at once. It just goes like splice, 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 splice as it comes down each of the fibers. Then
I have to do this engineering thing.
yes.
We like to draw a curvy line like that. That means it goes on for a long way. That's how you know that this isn't a square, it's a long thing.
Yes.
Okay.
Yes. And then we have a machine that shows a screen. It shoots out a laser light through each individual lines, and it measures out by distance the light loss of the line.
Oh, this is a graph.
Yeah, so that's it's facing towards me.
Distance.
Yeah, there you go.
Okay.
Yeah, so that
But how do you, that means you need to have an instrument at two different nodes that are far away, yes?
no,
you're bouncing there
it's
and back?
we're bouncing the light going through, and it's hitting a dead end, and it's bouncing back.
Oh, that's so neat. So that dead end even could be just a clip.
Correct.
Like,
So
like you could
every-
just snip it anywhere.
Every amount of loss,
That's creepy. You could
That
even
is-
measure how far away somebody had clipped it.
exactly. We can measure it down to the exact footage, or the exact millimeter. But that's what one of our machines does, is that it measures from the hut. There's always going to be a level of loss from the hut, but then it stabilizes out, and then we zoom in onto that portion where the light has been disrupted,
Oh my gosh.
and that's
Okay,
how
neat.
we determine how much of a dip we get, because sometimes the dip is something just very like minute, like the graph can go. I used to draw this way.
Draw for your own perspective. And then
Yeah. And sometimes it can go like straight, and then just dip ever so slightly, straight, and then blah, just go
Yeah.
like that.
Okay.
So you just
And-
have to test out in the field at multiple areas to find where this is happening.
Sometimes we can isolate it down to whatever footage this is, so we can say it's between like 800 and 900. I'm just writing backwards.
I'm thinking, how can you
There it is.
measure only to a partial distance instead of all the way to a terminal and back? Like, how would you know?
We take this distance, and the machine measures the amount of light loss. So say that this was
Yeah, but your instrument's only at this end, right?
yes, and it's shooting a laser that way.
So
all the
how
way
would
down.
you? What I'm thinking is, this is many data points.
Yep.
You know, okay, what's our attenuation at this location, and what's our attenuation here? How did we verify the location of this level of attenuation?
by the graph. So the machine, remember, the machine is shooting a laser light through the entire line. So whatever gets reflected back is what it's reading.
Okay, I bet I'm sure there's a lot more science into building that machine
Yes.
such that we can. If anyone in the audience knows, I'd love to know how we can get so like just like an electrical wire, you can measure the resistance of something, the whole length of wire, but you can't say where the resistance was peaking.
You know how auditory sensors work, where they shoot out a high pitch noise, and whatever bounces back is how they image a room. So that, like, say someone enters the room, the high pitch audio device can catch it because it bounces off at a later frequency. Same thing happens with the light inside the fiber itself. It can detect all the inaccuracies, all the like the faults within it, all the breaks within it, everything.
That's awesome.
So it's able to map out all of that. And what I was saying is that the machine itself, you can like focus in on how much light level loss this particular drop is going, because the machine has already measured out the entirety. Light travels pretty fast, so the machine measures this out already. You just have to figure out, okay, so in between 800 and 900, I get a certain amount of dB loss. That's the measurement which we use for light level loss.
Nice.
And so you go to where it's like, okay, we find in this neighborhood that it's in between like this terminal going to that terminal going to that terminal inside the neighborhood.
There's many branches off of here with nodes that come off of it. So
Correct.
they could ping a house that branches
correct.
off of this, and we know there's only 100 feet over to that. So it's sending loads of signals to loads of nodes. Okay.
And remember the augment hut that I was pointing at? What we do is we plug directly into this, where this guy plugs in, directly into that port. And so that graph is what you see is reading off of that port. That particular main line is what we call it, feeds a certain main line in the neighborhood. So it's a specific for specific main line. Typically we have 2 of those ports, and that signifies A side and Z side.
I'm partly not following, but I think to cover that area, we could use more like graphics and visuals. I think there's a little bit of helpfulness coming from this, but we don't have to.
No, that's a bit more technical, but that's basically it.
Awesome. That's probably where we'll wrap up the video. So thanks, Peter. This was an awesome explanation. And if you guys have questions, then boy, if you answer them in the comments, maybe Peter can log in and have some more discussion.